All right, hello everyone. Welcome back to Historical Geology 1404. Today we are discussing the Carboniferous and Permian. Let me widescreen this here. All right, before we start all that though, as per usual, any interesting updates, thoughts, stories, facts? Funny jokes, maybe?
Have you seen the people that have gone missing, the scientists?
Who are you talking about?
Have you seen? It's, I don't know what it is. It's like a bunch of NASA's, right? NASA?
I think they were NASA, but they were scientists who, I think they were like doing something with batteries, right? And like they all died like mysteriously.
Like this week?
No.
I don't know. I don't think it's this week because I've been hearing about it. But let me see if I can.
Yeah, please find me a source on that. That's very interesting. That hasn't come to my radar. You know what makes me think of though is there's a great show out there called The Three Body Problem on Netflix.
Compared to that.
Did they really? So in this show, certain scientists are having visions, and it'll either drive them insane, or they'll understand it and be able to like follow the instructions of the visions. I'm trying to give it to you without too much like spoilers. But like the ones that go nuts, they'll like claw their eyes out and like use the blood to write things on walls and stuff. But it's like a whole bunch of astrophysicists and quantum physicists and gravity experts and things like that. That's what this reminds me of.
One of the scientists' names is Amy Eskridge.
Eskridge? I don't know that I've heard of that one. But she's dead or missing.
Yeah, she's missing.
She's
No,
missing.
she died.
She died. When was this?
Oh, this was like from 2022, I guess.
Okay.
To now.
Okay, so what's happened is a couple of NASA scientists have died over the last few years, and people are wondering if it's some kind of conspiracy, maybe?
That's what I think. I feel like
Because they were all working on the same or similar topic, I think.
Okay, so there might be something there, but have you ever heard of the Curse of King Tut's tomb? You guys ever hear of that? Huh? No? The Curse of King Tut's tomb, when they found King Tut's tomb in, what was it, like the 50s or 60s? People were like, there was like all this folklore coming down through the native Egyptians that, hey, you don't disturb sarcophagi and their associated things or you get cursed, right? The gods will curse you. And so they went in there and, they were studying it and yeah, they were touching stuff and, King Tut's sarcophagus has been removed and all this stuff. And so people were like, ooh, they're all cursed now. And then one by one, they would die of natural causes, I believe. But it was like all over the course of like a 25-year period they died. And then when the last one died, they were like, King Tut's curse has been satisfied. I'm like, saying that 7 or 8 people who died over the span of a 25-year period were cursed, and like that's evidence that they were cursed, that's coincidence. That's not evidence. That's not the same thing. So it's probably something like that is what I'll say, right? A couple of scientists who worked on the same project dying over a couple of years is kind of suspect, but it doesn't have to actually be anything, is what I'll say. But the tabloids will absolutely make it seem like it is because they love a good conspiracy theory. Yes. And again, there might be something there, but I don't see sufficient data to suggest that there is yet. Thank you for bringing that up, though. Interesting. Okay. Let's see. As far as announcements on my end go, this is very important. Okay? I want to make sure that no one is confused by this. All right? So listen up to this part. This is the second to last week of the term, not the last week of the term. How many of you have gotten your graduation emails? You should have gotten it last week. They sent us all the email like early last week and said, hey, this is the message we're going to be sending to all the students in a few days. Check your emails. If you haven't got it, hopefully you get it today because graduation is next week. But that's my point though. We still have class next week. because of the really weird way they decided to do graduations this year, it's kind of throwing everyone off and making a lot of confusion. So I'm going to say this in as little as confusing as possible, okay? We have class today. We have class on Wednesday. Next week, aka graduation week, we still have class on Monday. Some people are graduating on Monday evening. We still have class on Monday. We still have class on Wednesday. Some people are graduating on Tuesday evening. Some people are graduating on Wednesday evening. We still have class on Wednesday. That day is going to be our kind of class movie day for the extra credit, right? And / get done anything that you haven't gotten done yet in my class and others, right? Kind of I don't want you to think of it as a free day because you are still required to be here. Those of you that are in high school, you will still be required to be here that day, okay? Then some people are graduating on Thursday, and then some on Friday, and some on Saturday. All of that next week, regardless of the number of graduations going on, classes are still happening, and you will still be required to be present at those classes, whether you've graduated already or not, okay? It's a really weird situation. And again, I don't really understand the reasoning why they are making us do graduation every day of the week. But here we are. All right, so no confusion about that, right? Clear as much as it can be anyway. They have declared next week to be finals week and graduation week, but that does not change class schedule whatsoever. All right. Any other questions or any other comments before we begin?
Why did they decide to do it over at the sports center?
That is the best question that anyone could be asking about the situation. And the answer that I give you is the answer I was given, and at least in my mind is absolutely not a satisfactory answer. When they first introduced this to us, they said, hey, we've gotten a lot of feedback from the community. They tend to like it better when we have graduations at the sports center. It feels homier, it feels smaller, it feels more like a community. The Coliseum, it gets so full, it's so big, it's hard to tell, it's hard to see from the back. You know, it's too big. So we're going to have all the graduations at the sports center. It's like, oh. So we went from having 3 packed graduations at the Coliseum, which sure may have felt impersonal, but got people in and out, which is what most people care about at graduation anyway. Give me my piece of paper and let me go enjoy my time with my family, right? That's what most people want. So now we're having 9 ceremonies at our much smaller facility here to make it homier and cozier and more community friendly. My own suspicions on the matter are the cost of reserving the whole Coliseum for a weekend was something that they didn't want to front this time around. I've heard estimates for how much it costs to rent the Coliseum for a whole weekend. It is a crazy amount of money. Let me move that box. I'm sorry. I left that there after the reptile show this weekend.
Oh, did you go?
Yes, I had a table. I took Diablo, I took Algernon, my box turtle, and I took a bunch of fossils and minerals to show people as well. It was fun. Yeah, so I don't think that they wanted to pay the bill for the Coliseum. I think that's actually what it came down to. It was a business decision, I'm pretty sure. That or someone really dropped the ball and didn't reserve the Coliseum in time, and they're trying to play it off as a favor to the community even though someone forgot to make the phone call and reserve it. Those are my 2 biggest suspicions here. We will see. Oh gosh. Oh, what the heck. I'm usually pretty blunt and straightforward with you guys. I don't beat around the bush that often. I don't think that the whole graduation week idea is going to pan out the way that they want it to. So I would bet we probably go back to the normal version of things next year.
They have to do it when we graduate.
They have to when you graduate? I hope they do. We had a pretty good system then. We have so many graduates every year now. We have 9 ceremonies because we have 1,800 graduates this term. Which, I mean, would basically take us from having 3 ceremonies at the Coliseum to 4. We would have 2 on Friday probably and 2 on Saturday instead of 1 on Friday and 2 on Saturday at the Coliseum. Maybe that was the reason why. Maybe that extra allotment of time was just something that they didn't want to pay for. I don't know. I think I don't think it's going to go as well this weekend or next week as they think it will, though. For those of you that are graduating, I'm sure it's still going to be a wonderful, beautiful experience. You're still just going to be there for your hour, hour and a half, I think. I think you're each going to be in groups of maybe 150 students that are graduating with you. It is going to feel cozier, and it is going to feel homier. It's going to feel packed, I would say, especially on the nights that have the graduation with the most students. And this is probably most of my observations here kind of come from a selfish sort of perspective because as a faculty member, I have to be at all the graduations. So it's going to be cozy and packed and homey for me for every evening and all of Friday and all of Saturday. So, hooray. All right, enough about graduation, unless anyone else has any other questions. Good question. I'm not sure how they're going to do it this time around. Check-in for students, that's all going to be in the email. And all the information, if you haven't gotten that email yet, you can go to the OC registrar's website, the registrar's part of the OC website, and all the information should be there. They told me it's been posted there. But where was check-in before? Check-in for students was at a table right as you walk into the sports center. And then I think that they had all the students, yes, they have them all go to the ICA gym. Okay, so you check in, and then they direct you down to the ICA basketball courts across from the weight room. If you guys have ever been to the sports center, right? I know where you know what I'm talking about. We're there every morning. Okay, so the ICA courts, basketball courts, they are already got the carpet lined out there, and they're just going to set up the chairs so that they can keep all the students there, and then they will put you in a very specific order. The order that you are sitting in the ICA gym is the order you're going to walk down the hall, down the stairs, and to your chairs in the main basketball court, okay? And that's the same order that they're going to read your names off of. So they're going to be very strict with you about the order you are walking in and that you stay in your specific chairs. So yeah, check-in should be there. When it's at the Coliseum, you have to check in at a totally different barn and then walk across the Coliseum parking lot to get to the main facility there. Yeah. Good question. Anything else? They usually have you check in, I think like an hour. They ask you to be there an hour before the ceremony starts. So I guess my estimate for how long the whole thing would take, I should probably tell you it'll be closer to 2 hours because you go check in an hour beforehand. Then they're pretty prompt. They're pretty on time with getting people in, sitting people down, and then they read off the names. And then once the names are done, President Williams gives a spiel. People are happy. They'll pop some confetti, and then we'll all file out. And that's that. Okay? And I'm going to be there for every graduation except Tuesday. So whenever you're graduating, I'll high-five you on your way past me. Okay? All right. Anything else? I always sit in the front row so I can high-five my students. All right. Well, then, let's jump on in. So we finished off last time. Do you remember what the last time period we learned about was? The Devonian. Thank you. Okay. The extinction at the end of the Devonian, right? We lost some things, some corals and a few other organisms. The Carboniferous is where we're picking up today. The Carboniferous is called the Carboniferous for the reason that the most you can kind of think of the Carboniferous as like the age of plants. And I know that's going to sound weird because we already talked that there were plants before. There are plants now, but there have never been more plants spread across our planet than there were during the Carboniferous. The sheer amount of plant biomass on the Earth was extraordinary. Matter of fact, and how do we know this, by the way? First of all, coal beds. Coal beds. Remember what coal is? Okay, coal is compressed plant matter that is refused the opportunity to decay. It gets buried too quick, or it falls into an anoxic environment when it dies. So instead of decaying to bacteria, it just kind of hangs out, and its organic components turn into coal. Okay? So massive, massive beds of coal come from this time period. I'm talking 30, 40, 50-foot thick coal beds here. And when you think about how compressed that all gets from the plant matter it was before, we're talking hundreds of feet of plant matter that just fell on top of itself. Okay? For millions of years, it was like this. But also, an interesting phenomenon that happened here because of the plant life. What does plant life produce? Huh? Oxygen. Bingo. What does oxygen do? What's one of the effects we've learned about that oxygen can have? Huh? It can rust. This is true. Not what I'm fishing for here, but that is good. That is true. Huh? How does it cool things down? How does it cool the environment down? Plants suck in the greenhouse gases, and they spit out the oxygen, right? Oxygen is not as disruptive to solar radiation reflection, right? And so we tend to lose more heat. We retain less heat as a result of the amount of oxygen in the atmosphere. So we're going to see during the Carboniferous environmental fluctuations. That's true, but there's also another thing. How much do you guys know about fire? Do you know that fire is a chemical reaction? It's a form of oxidation. Which means, what do we need for a fire? What are the ingredients we need for a fire? Any of you ever Boy Scouts or Girl Scouts? No?
You need a spark, right? And then some dry material.
Okay, you need fuel, that dry material. We need a spark, which is heat. What else do you need?
You need the
Oxygen. Fire will not exist in a vacuum. That's why I love watching the Star Wars movies. Even the modern Star Wars movies will still have explosions in space whenever a ship blows up. There would be no explosion because there's no oxygen to consume, right? There might be a brief one when it consumes the oxygen inside of the spaceship, but not as big as the fireballs that we see in the TV shows, right? Or in the movies, okay? There is no oxygen in space. There would be no fire, okay? Without oxygen, there's no fire. What are the plants producing? Tons of oxygen, lots of oxygen. So that affects the environment, but also it makes forest fires incredibly common. We see in Carboniferous layers of rock so many not fossil fires, but fires preserved in the fossil record. Tons and tons of just carbon deposits. Carbon, which was the ash left behind by the fires as they burned up incredible, massive quantities of forest. One lightning strike, kafoom, right? Forest fire. Takes very little effort. Right now, I mean, it's pretty easy to start a fire right now, but imagine with even more oxygen in our atmosphere, way, way easier. Okay? So lots of forest fires going on here. Now, the Carboniferous is separated into two sections. The Mississippian, from 359 to 323 million years ago, and the Pennsylvanian, from 323 to 299 million years ago. I'll talk about why that separation here in a little bit. Spoilers, it's environmental. Okay? All right, so the big thing that was happening here, starting in the beginning of the Carboniferous, plant life. Plant life went everywhere. Okay? Not only is it everywhere, it's also looking a lot more to what we have now. Okay? We see things that look like modern-day trees. Ferns are everywhere. Okay? We see all of these things. You would walk through a Carboniferous forest, and it would kind of look pretty similar to a rainforest sort of situation that we would see today. Excuse me. Upon closer inspection, you would see that none of the plants actually are the same ones we have today. But a quick glance, you would think, oh, okay, I'm walking through Western Washington right now, right? Okay. Now, in the oceans, ammonoids make a strong comeback. Okay, we see a lot of them, and they start getting bigger. We start seeing things like there's more elaborate sutures in their shell patterns. Okay, they start showing up during the Carboniferous. We also see a trend. Up until this point, most of the, oh man, I need to remember to do this. Most of the arms race has been who can get the thickest armor. And if you have the thickest armor, your predators need to get thicker, bigger, stronger teeth or jaws or claws. And then you just make bigger armor. And that's followed by bigger teeth, stronger teeth, so on and so forth. Armor has kind of been the name of the game when it comes to the arms race. In the Carboniferous, we see a general trend in another direction. We see fewer things evolve towards the more armored evolutionary path, and more things start deviate towards speed, mobility. Okay, less what's a good example here? Less, I guess, that was a bad example. Less turtle, more leopard, you know? Something that's fast enough to catch its prey, or something that's fast enough to escape, something that's less likely to just rely on its shell to defend itself. Okay, our brachiopods got hit pretty hard in the Devonian extinction, but they do come back really strong during the Carboniferous, and they stay strong. The bivalves are hanging out. They are still living in a lot of the same ecosystems as the brachiopods. They're more or less cousins to each other. Okay, they're getting more and more separate as time goes on, but they're still pretty much evolutionary cousins to each other. So they occupy a lot of the same niches. Just during this time, bivalves still holding fast to that second fiddle position. Okay, but their time will come. Just wait a little bit. Now, crinoids. I kind of told you about this last week. When we were talking about the development of crinoids becoming more of we'll see them in more groups, less solitary organisms, like what we saw happening during the Silurian and the Devonian. Well, if on land we are experiencing the age of plants, in the ocean, the Carboniferous was the age of crinoids. Vast prairies of crinoids out there in the ocean. Okay? You go scuba diving out there in the Carboniferous Ocean, and it would just look like a grassland full of crinoids. My paleontology professor for my undergrad, his name is Forrest Gahn. He is one of the world's expert in Carboniferous crinoids, and he made sure we got plenty of hands-on experience with those things. He took us to some fossil formations where they were literally just, it looked like most of the rock was made out of crinoid pieces. There were so many of them. They make up incredibly thick layers of crinoidal limestone, we will call it. You guys even saw that at one point in one of your labs, okay? Crinoidal limestone. So thick, full of crinoid fossils that's pretty much what it's made out of, okay? All right, our reef systems collapsed during the Devonian extinction. Because of that extinction, because of the environmental factors that caused that extinction, there was a shift in ocean chemistry. Now, we've talked a little bit about this. You shift the ocean chemistry, your organisms that rely on that chemistry to make their shells and skeletons and things like that, they're going to get hit pretty hard, okay? So what was, what the species were that were relying on that chemistry pretty much all died off, were reduced in numbers to the point where other things that were able to adapt to the new chemistry came back faster, okay? So our tabulate corals and stromatoporoids, they never came back from that. They hang out for a little while longer, not too much longer, but they do hang out for a little while longer, but they don't make the core of our reef systems anymore, okay? And unfortunately, our placoderms, our big giant armored fish like the Dunkleosteus, right, with the skull bones that fit together like crafting scissors, you remember that? They're all dead, leaving behind an open niche space, right, for predators to fill. The apex predator positions, now wide open. Our foraminiferans, so those tiny little planktonic creatures, right, that we rely on so much in things like the oil industry for analyzing rocks, and that are responsible for making a lot of the oil that we pull out of the ground, out of ancient marine deposits, okay? In the late Carboniferous, we see a pretty big explosion in foraminiferans. A new type is introduced on the scene called fusulinids. You've already seen these in a lab. Okay, the ones that look like big pieces of rice. Those are fusulinids. Those are one of the largest species of foraminiferans ever to exist. Okay? And they make for fantastic index fossils because they did not live for very long. Okay? So you find fusulinids pretty characteristics if you're looking at Carboniferous age rocks. All right, let's talk about those plants on land. All of the plant life, when you go from just piled up plant matter to coal, while all is considered, reduces by about 30%. So it takes about 3 feet of plant life to make 1 foot of coal. So when I'm talking about a 30-foot thick layer of coal, we're talking 90 to 100 feet of plant matter that got compressed down into that. It's an impressive amount of plant life. Remember what I told you about the rainforests that exist today, where their roots don't go very deep because they mostly just cycle nutrients from the dead stuff that was in the generation before them, right? Grow a plant, it dies, boom, nutrients go into the topsoil. Another plant, or I should say more like 10 plants, grows, utilizing those nutrients, so on and so forth. So they just pile on top of each other, and that's how you end up with these thick coal deposits after all those years. We did see the development of woody tissues in plant life before, particularly the trees, before this point, but we are still not entirely to the point where everything is wood. It takes time for adaptations like that to work their way through the community. Okay, for the ones that have the most rigid tissue structures, like the woody structures, to be big enough of an advantage that they pretty much take over that ecosystem, replacing the ones that cannot cope or adapt as quickly. Okay, so they're still common, but they are not the only ones here yet. Let's see, a lot of ferns, a lot of things that look like horsetails. If you guys have ever seen horsetails, like next to a lake or a marsh or anything like that, those are what modern day horsetails look like. We find ancestors of those in the fossil record from the Carboniferous. All right, gymnosperms show up in the Carboniferous. Gymnosperms are extremely important. Gymnosperms have a very wide adaptation, okay, a very widely adaptable capability. Today, gymnosperms are very common in higher altitudes and cold environments. Some common gymnosperms you might be familiar with: Christmas trees, right? Those pine trees, firs, those are all gymnosperms. Very common gymnosperms back during the Carboniferous and then later on during the Permian and Mesozoic, right? Ginkgos. You guys ever seen a ginkgo before? No? We find ginkgo fossils from layers of rock all over the world. But for a long time, no one found any living ginkgos. So this is an example of an organism that people for a very long time thought were extinct, until Europeans made their way to inland China, and they found that there were groves of ginkgo trees being kept alive by Chinese monasteries. They were being kept alive and cultivated for medicinal purposes. And so this is an example of an organism that for a long time people thought was extinct, but then turned out to still be alive somewhere. And ever since then, these have spread out all over the world again. You can go to your local plant garden center and you can buy ginkgo seeds to grow one in your own backyard, right? They made quite the comeback thanks to humanity. All right. Now, gymnosperms mark a very important point in plant evolution. We've already seen how plants have gone from having spores, from spreading via spore, like a fern does still, to seeds. What was the advantage of going from a spore to a seed? Why could they spread out more? The seed sprouts little legs and travels further? Let's do it. Yeah, it's walking away. Yeah. The wind? Yeah, sure, wind could carry it, but it can carry a spore further. What's the advantage of a seed over a spore? Both are reproductive methods.
Is it like the seed more protected?
Protected how?
It has that layer.
Yeah, it has a hard outer coating that protects it from drying out. It protects the insides from drying out. A spore has to be wet all the time. That's why mushrooms grow in your yard when it rains, right? They have to be wet for it to grow, for it to survive. A seed, though, I mean, you can buy packs of like carrot seeds. I planted some carrots with my kids last month in a little garden plot in our backyard, right? Just little dehydrated seeds that you just drop in and you water them and they're totally fine. They'll start growing, right? Seeds have a much bigger advantage, okay? Now, gymnosperms are seed producers. What they bring to the table, though, we see a development of new methods of spreading these seeds. Things like conifers, okay? So those pine trees, those firs, things that make cones, okay? When you see a pine cone, you usually see them when they're all spread out. That's what happens as they dry. What they are before is they're very hard, kind of like a rock. Imagine if you take that pine cone and you put all of those spread out pieces together, you get something that's kind of shaped like a bullet, okay? And as it's growing on the tree, this pine cone is growing the seeds inside of it. Once that pine cone reaches maturity, as the seeds inside are ready, they have reached maturity, that falls off the pine cone, it'll roll away, and then as time goes on, as the season progresses, it'll dry out. As it dries out, those pieces of pine cone peel apart from the center, releasing the seeds that were inside protected by it. It's another level of protection for this organism. It's amazing. Which means that conifers and other gymnosperms that had similar abilities were able to spread even further inland. And this is a big part of the reason of why the Carboniferous was so plant-rich. The interior of the continents were accessible now to plant life. Higher altitudes were accessible to plant life. Colder climates accessible to plant life through adaptations like this. Okay? So, our seedless vascular plants here in the Silurian are seedless vascular plants slash the beginnings of things like ferns and sphenopsids right here in the Devonian. And now we're in the Carboniferous. Look at how thick the number of genera are here. Lycopods, very, very common. Seed ferns, very, very common. Sporing ferns, very common. Sphenopsids, very common. Our conifers show up at the end of the Carboniferous. They become extremely common through the Mesozoic, which we will get to on Wednesday, and they continue through to today. But you know what you don't have here? Flowering plants, angiosperms. Those don't show up until almost the end of the dinosaur time period. We'll talk about those on Wednesday. There were no flowers during this time, just non-flowering plants, okay? Just green everywhere, right? Should I deviate for a second? You guys up for a quick tangent? Why do we see plants as typically green? Not all of them are, but like 99% of all plants are green. Chlorophyll, but what makes chlorophyll green? What color is sunlight? Well, the wavelengths that the sun is giving off is white. Our star is white. It appears yellow to us through our atmosphere because it's slightly diffused. But if you're in space, the star is white. We have a white star, okay? Which means the light is white. How do we know that? Because snow is white and paper is white and that shirt is white when it's outside, not just in here, right? We know that our star is giving off white light because white is a color that we observe off things that reflect that light, okay? Everything you see that has color is reflecting light. White things reflect all of it, which is why when you're walking out on the parking lot, the blacktop is really hot because it's absorbing all of it, and the white parking lot lines feel much cooler. You walk on the white parking lot lines. Can anyone else relate to that? I spent my childhood barefoot in Hawaii, so it's like I was walking around barefoot a lot in parking lots. Always walk on the white lines. Take my word for it. Way cooler. Now, if we observe color of objects because of the wavelengths of light, they are reflecting, not absorbing. We're not observing the colors that it's absorbing. We are observing the colors it's reflecting. What wavelength of color do plants not absorb? It'll be green. Plants are generally green because they are absorbing every other wavelength for photosynthesis. Why not green? That is an excellent question. It could have been anything. Maybe somewhere out there in our galaxy or out there in the universe, the progression of life occurred in nearly the exact same way. There are versions of plants out there, but due to some evolutionary fluke, they don't absorb red. Maybe all other plants are red. Maybe there's a planet out there where all the plants are purple. Maybe there's a planet out there where all the plants are black because they absorb every wavelength for photosynthesis. Interesting. Interesting. Okay. Now, what's going on in fresh water? Because what we saw happening during the Silurian and Devonian was life spreading into fresh water. Our brachiopods, our bivalves, sharks and rays, okay? They start moving out into fresh water, and sharks and rays in particular become very successful in fresh water during the Carboniferous. They also become very successful out in the salt water. Sharks start filling a lot of the niches left behind by the former apex placoderms. Okay, we'll see some sharks becoming larger, more successful out there. Clams and other bivalves, we start seeing freshwater clams, similar to what we have today. Okay, now, who likes bugs? The eye. You don't love them, don't hate them, just kind of hanging out. All right. Well, as the plants spread inland, they produce all that oxygen. That oxygen actually has another effect. Our insects that started showing up on land during the Silurian and have diversified during the Devonian have gotten quite large. This is a picture of Arthropleura. It is an 8-foot millipede. Yeah. Pretty big bug there. Look at all that armor plating. Clearly protecting itself from some kind of predator. We'll get there in a minute. Detrivore, though. Ate dead, decaying plants. Probably ate the occasional dead, decaying animal, too. But mostly plant life, just like modern-day millipedes, detrivores. Okay. Imagine dragonflies the size of a bald eagle. Yeah. This is what is going on. Bugs get big, and they grow wings. So they are dominating the skies when there is nothing else flying. The first animals to take to the sky were bugs. They were insects. Okay. So why the big bugs? Well, it has to do with oxygen. Turns out that when you increase the amount of oxygen in an environment, the insects that live in that environment, their breathing apparatus changes size. Increase the amount of oxygen, you change the size of the breathing apparatus in a bug, the bug's body has to grow to compensate for that. Because they don't cycle oxygen through their blood the same way that we do. They don't have the circulatory system that we do. Their breathing apparatus basically just delivers oxygen straight to wherever it needs to go. So as the amount of oxygen increased, the size of the breathing apparatus increased, which increased the proportional size of the bug body, okay, the insect body. And so that's why as the Carboniferous goes on, we see bigger and bigger insects. We've actually tested this. People have tested this in a lab. They took houseflies and they put them in an enclosed environment, and they slowly increased the amount of oxygen in that environment. And houseflies are a great thing to test this with because you'll get a new generation of houseflies every couple of weeks. Okay? They'll lay their eggs, the eggs become maggots, the maggots hatch into flies, so on and so forth. You just make sure that they have enough food. Okay? So over the course of generations, increasing the oxygen ratio in this enclosed environment, they developed bigger and bigger houseflies. Okay? Proven concept. Oh, when I say bigger, I don't mean like Mothra, right? No, I mean like maybe there was a 15 to 20% body size increase, right? Because to make something that big has to happen over millions of years. To do it in a lab environment, they tested over 10 or 12 generations of houseflies, and they saw enough of an increase to prove the point, but not enough to go, get there. Yeah. All right, now, why would this bug need armor? The only reason you have armor is to protect yourself. What was this thing protecting itself from? Clearly, insects are not the only game in town here. Where did we leave off with our vertebrates? They had just crawled out onto land. You guys remember our friend, the Tiktaalik? Yeah? The lobe-finned lungfish that pulled itself out on the land, and we have trackways of it, right? Where are they at? Let's see. These fish have pulled themselves out onto land. They can now live on land and in the water. Do you know what we call that? There's a word for that. Amphibious is the word for something that lives both on land and on water. And so we call these first organisms, these first vertebrates that were able to do that, we call those amphibians. And thus we see the first amphibians in the fossil record, okay, here during the Carboniferous. Now, they kind of look like frog lizards, right? And you can still see some of the fishy sort of characteristics, okay? You see eyes that kind of look like fish. You see the fins, some of them had still had flippers, kind of flipper-looking things. But this is where our amphibians are now. We've gone from that Tiktaalik that was clearly a fish that was able to pull itself onto land to this. Looks like a cross between that and a frog. Like if you look at my frogs over there, you would be able to see some of the characteristics here. As a matter of fact, I would encourage you to go over there and look. I would go grab one and pass it around, except that their skin is very sensitive to oils, so I hold them as little as possible. Okay, but you are more than welcome to go over there and look and see the characteristics here. Not a whole lot have changed. Leg placement, body size, head, still very similar to modern day frogs. Okay? Now, amphibians, these things started filling in a lot of the apex predator spaces on land. They didn't have much competition except for those insects. Okay? Those insects. And it just so happened that those insects were their main food source as well. That's why Arthropleura was armored. Some of these amphibians, guys, got 20 feet long. Imagine a giant amphibian, essentially a long frog the size of a saltwater crocodile, chasing you down. That's what the Carboniferous would have been like. And yeah, it would have chased you down. Amphibians today, like my frogs, they are opportunistic feeders. That means that anything that moves that could fit in their mouth, they will try to eat, including other frogs. You go near a 20-foot amphibian, it will try to eat you, right? So that's what this would have been like. Don't recommend. Find another vacation spot. Now, that's amphibians. As we move on through the Carboniferous, something incredible happens. Amphibians are an incredible evolutionary product, okay? But they're still limited. They have one big hang-up. What is that? Have to be near water. Their skin has to stay moist, and so do their eggs. They lay eggs in water. So do modern-day amphibians. My frogs have a male and a female. People ask me all the time, do they mate? Do they lay eggs? And I can say no. Why? I don't give them enough water to lay their eggs in. So they don't. If I gave them enough water, sure, they would mate and lay eggs. I refuse them that opportunity. This is the big limitation that amphibians have. They need water for eggs. So, for a while, amphibians just hold their ground on the coastlines and near the river systems. But then, there's a mutation. An amphibian has a mutation where its eggs are grown, are produced, are born with slightly thicker shells. Advantage? Maybe not initially. But it allows that amphibian to lay its eggs on the beach instead of in the water. Right? Near the water, moist. Not in the water, wet. Okay, great. Then the mutation continues. Maybe it gets bigger. Maybe another mutation changes the shell's chemistry. So you have the combined genetic mutation of thicker shell combined with maybe we're going from a thin filmy shell to a calcium shell. Now my shells have a thicker barrier, right? That's great. Then there's another mutation. Amniotic fluid. You guys know what amniotic fluid is? It's the white stuff in the egg. Yeah. Not the yolk, it's the white stuff. This is the development of the amniotic egg. The amniotic egg is a completely self-contained, self-protected package within which an animal will grow. It does not need anything from the outside world. Amphibian eggs require the presence of water to keep them safe and keep them wet. Amniotic eggs don't need that, right? You guys like eggs, chicken eggs? That's an amniotic egg, okay? Now, your yolk eventually turns into your embryo, and it has everything it needs in that yolk and in the amniotic fluid out here to keep that embryo safe until it's ready to be born. Now, this allows the amphibians to do something very important. If they don't have to lay their eggs in the water, they don't have to stay in the water. So they leave. And so these hard-shelled amniotic eggs allow amphibians to move inland, and as a result of needing to walk more, the leg placement starts to change. Leg placement starts to change. We see a lot more developments changing here, which I'll go over here in a minute. But this is important because this is the beginning of the next important section of vertebrate history, reptiles. Reptiles came from amphibians that had the positive mutations that led to the amniotic egg. Now, I want you to think about this for a second. Can anyone draw a comparison here between what just happened from amphibian to reptile and what happened to another group of organisms we already talked about? What does the development of the amniotic egg sound like to you? Well, it's part of that sequence of animals on land. Can anyone else think of something this sounds like? You went from a soft-shelled, needing to stay wet all the kind, genetic package, to a harder-shelled, easier to live out on land. Spores to seeds. Do you see that comparison? Yeah. Right? Is that still a meme? Does anyone still use that as a meme? No? No? All right. Mind-blowing, right? It's the exact same thing. What happened to plants 100 million years ago is now happening to animals. The same concept. And why? Because the same physics, the same chemistry, and the same environmental rules apply to plants and animals alike. It's just that animals are spreading out later than plants. Plants went on land first. They were followed by the animals. Seeds develop first in plants. Hard-shelled eggs develop second in animals. The same positive mutations are true in both types of organisms. In this particular case, we'll see that sort of convergence in evolution happen throughout time. Okay? All right. Any questions about the eggs? Anything like that? This is huge. All right. Let's talk about the Carboniferous tectonic situation. Here we are in the early Carboniferous. We still have Gondwana land as our supercontinent here. Euramerica over here. Siberia just kind of hanging out by itself. North China hanging out by itself over here. But here in the middle, we get this protected sort of ocean zone. This is called, it's going to be called the Tethys Ocean later on. Right now it's called the Paleotethys. It hasn't quite finished because what's going to happen here is Euramerica is going to connect down here. North China has a chain of islands that connects it up here to Australia. And this is eventually going to become Pangaea. Here in just a minute, when I flip the slide, we're going to see Pangaea form, okay? And making what will be the Tethys Ocean here. And the Tethys Ocean, think of like the Gulf of Mexico times 10. Protected from the rest of the ocean, a few inlets allowing water in and out, but the perfect living space for life. Stuff lived in the ocean out here all around the rest of the world, but the amount of life that was teeming here in the Tethys, what will become the Tethys, made a ton of fossil beds. Okay. All right, so here we are. On Gondwanaland, right as Gondwanaland and Euramerica collide, they're going to make that Pangaea. Okay. That's going to be part of the Wichitan orogeny is going to happen there, followed by the Alleghenian orogeny. Okay. So the Wichitan, that's how you pronounce that, Wichitan. Okay. I know it looks like to be Ouchitian. It's Wichitan though. Okay. That's where South America and Laurentia come together. Okay. So here we have Laurentia. Here's South America down here. The collision of these two right here to make Pangaea was the Wichitan orogeny. Then Africa right here and Eurasia right here collided. So we see kind of this chunk here and then a rotation and another impact right there. Okay, so those are the two orogenies you need to know about for the Carboniferous. Early on in the Carboniferous, very warm, very wet climate. Then as the plants went and did their thing, we saw a few ice ages, right? We saw a lot of temperature fluctuations. And that's going to be what makes a lot of the micro-extinctions we see in there, including one in the middle of the Carboniferous. That's why we separate the Mississippian from the Pennsylvanian here, okay? So lots of glaciers here. As a matter of fact, look at this. So this is from the late Carboniferous as we're moving into the Permian, okay? So this isn't an image specifically of the one between the Mississippi and the Permian, but same sort of concept here. Look at how much of the bottom of Pangaea is covered in ice, okay? There was some extremely cold weather going on down here at the bottom. Matter of fact, here during the Carboniferous is the first time that we can positively identify in the fossil record that there were polar extremes here. The amount of oxygen in the atmosphere, the differentiation of gases between the equator and the poles means that we are seeing the first evidence of extremes. Okay, so we have extreme cold here and extreme hot in the equator, just like we do today. Okay, very similar climate to today. Less of the whole world is warm or the whole world is cold like we've seen in the past. Okay. Any questions about the Carboniferous? All right, well then let's move on to the Permian. The Permian sounds very similar to you guys, right? Sounds very, very familiar to you, I should say. Why does the Permian sound familiar to us here? Yeah, we live in the Permian Basin. Anyone want to take a guess as to why the place we live in is called the Permian Basin? Yes, it was a basin that got filled in during the Permian. Yes, yes. This was a shallow sea at one point, and it got filled in by sediment as time went on. Okay? We call it that because the sediment that is here was put in place, and because of the nature of the basin that sediment is inside of, oil does not really migrate out. It's gotten trapped here in this perfect place for looking for oil. Okay, so the Permian. On land, we see some really big changes happen. Our reptiles, having survived through the temperature extremes at the end of the Carboniferous, become extremely adaptable. Okay? Reptiles have a big advantage over the amphibians. Now, the amphibians are still here, but they're still restricted to coastlines and in the waters. Okay? The reptiles, being able to move inland and having a wider range of habitats to expand into, they become extremely adaptable. The reptiles gain some new characteristics, some new traits that give them distinct advantages. Okay? Jaw structures. Our amphibians' jaws, I already told you this, kind of like frogs today. They don't chew, they don't even bite hard. They just close on their prey, stuff it in their mouth deeper, and then swallow it down. Usually live, right? So the stuff that my frogs eat still goes down into their stomach live. That cockroach we fed it, right, last week, that Emma helped me catch, went down the hatch, still alive. Okay, kind of horrifying when you think about that, but there it is. Okay, we see the development of jaws in predatory reptiles specifically for biting hard, not chewing. We're not quite to the point where they would chew, but they bite hard enough to kill, to rip flesh from their prey, or to strip leaves from branches. Okay? They don't just stuff things in their mouths anymore. Okay? We see a type of reptile show up on the scene called a pelycosaur. This is an example of a pelycosaur right here. Did you guys ever get dinosaur toys when you were a kid? Those little tubes of dinosaur toys, do you ever see those? Like at museums and stuff? They always have one of these in there. And it always pisses me off professionally. Because they put these in there with the dinosaurs. But we don't have dinosaurs yet. We're still in the Permian. Pelycosaurs like this are the ancestors of what will become dinosaurs later on in the Triassic. Okay? Now, what do you see on its back here? Yeah, that fin. Okay. Right. Let's talk about this. Why would something grow that massive, obtrusive fin? You can't fit under an overpass with that thing. Why would you have a giant fin on your back? What are the advantages? There has to be an evolutionary advantage, or else it would have been here and then gone again. We probably wouldn't even have a fossil record of it, because only a few individuals would have had it before dying off. But it was such a successful trait that the entire species thrived during the Permian. Okay? This is called Dimetrodon, by the way, this particular species right here. Notice some of the changes. Before we come back to that thought of the fin, be thinking about that. I want to point out a few changes. These amphibians that this pelycosaur is harassing right now, look at them. Look at their head structure. No musculature for a strong bite. Look at his. Look at that broad, tall head, filled with muscles for biting, with long, sharp teeth, meant for snipping, right? Meant for grasping and tearing. Look at the legs. The placement of the legs on my pelycosaur is more under the body, whereas with these amphibians, it's still out to the side. Okay? Okay, now let's come back to the idea of that fin. What would that fin be used for? What was the one you just said? Warming the blood. How would that work? You pump blood up through this thing, warm it in the sunlight. Why would that be an advantage? Amphibians and early reptiles, yes, they were cold-blooded. Why would it be an advantage to be able to warm your blood up faster? Bingo. Bingo. You're an amphibian. You chill out here on the banks of the river for an hour every morning before you have warm enough blood to get going for the day and start looking for food. You're a pelycosaur. You stick your fin out in front of the sun for 20 minutes and you're good to go. You have that 40-minute advantage on any prey you want to hunt for breakfast. Okay? Huge advantage there. That's the most likely scenario for why there would have been a fin. There are obviously other options, right? It may have had something to do with sexual favoritism, right? Whoever has the biggest or brightest colors on your fin, I prefer you as a mate sort of thing, right? That's always an option. Every species, well, not every, but a ton of species will do something like that, okay? Think peacocks, right? All right. Then, after the development of the pelycosaurs, which were very common during the Permian, okay, apex predators, at the end of the Permian, we see these things called therapsids. Therapsids come from these pelycosaurs. They keep their strong bite force, but they develop broader jaws, okay, and specialized teeth. What do I mean by that? How many types of teeth do you have in your skull? The molars at the back. Yeah, the canines, right? Your pointy ones at each corner. Okay, more like for cutting, right? We tend to use those for cutting, right? The incisors here at the front, okay? The flat ones. We have 3 types of teeth in our mouth. Right here with these therapsids is where we start to see the development of specialized teeth for various functions, okay? So you can see they've got those thick canine-looking things at the corner of their mouths, just like we do. Then they have smaller ones, which granted are still more like canines than anything here at the front. And then they don't have chewing molars back here, but they definitely have shorter, broader, sharp teeth. Okay? Previous to this, the Pelycosaurs, they just had the sharp teeth all around the insides of the mouth. Now, not everything that descended from these kept the specialized teeth. It just so happens that these therapsids are the ancestors to mammals. And fossil evidence would suggest that perhaps they also were endothermic. They were able to regulate their own body heat, possibly. Okay? So we see the development of distinctly mammalian characteristics here. Okay? By the way, there's two here presented, and they kind of look very similar to each other here. Therapsids had very similar body structures to each other, at least initially. This is an herbivorous one with blunter, snipping teeth meant for plants. This is a predatory one who's going to go snack on that one with those canine teeth and more claws on its legs and such. But it's got more vertical leg placement than the Pelycosaurs did before it. We're seeing the development of more modern characteristics that we will see in animals today. Right. At the end of the Permian, this is the biggest extinction that we have in the fossil record currently. There may have been a bigger one. We may find evidence that one we thought was pretty big before was even bigger. But as of right now, as we have uncovered in the fossil record so far, this is the largest extinction that has ever happened on our planet. 80% of everything in the ocean and 70% of everything on land died. Now that's species. That's not quantities. An estimated 99% of every individual may have died from this thing. But 80% of all species in the water and 70% of all species on land died. Unfortunately, we have to say goodbye to our friends the Eurypterids and the trilobites at this point. I know, the trilobites. They held on so long, they couldn't survive this one. Okay? They couldn't keep up. So, what happened here? Well, there is some evidence in the carbon and oxygen delta carbon oxygen 18 and delta oxygen or carbon 13 ratios, which that's basically just saying what the ratios of the standard isotope to the other isotope are. You would compare carbon 13 to carbon 12 and oxygen 18 to oxygen 16 for this sort of study. It's exactly what I did in my thesis for my master's degree. You can see right here where there is a massive spike in both of these at the end of the Permian. Ka-chunk, ka-chunk up in both. Yeah. So that tells us huge change in temperature. What could have caused such a massive temperature spike?
It got hotter or colder?
It got hotter.
And it got colder.
I mean, yeah, it was both. There's usually extremes follow each other. Yeah, check this out. Here we have Pangaea at the end of the Permian. Okay, so Pangaea has fully formed. Here's that Tethys Sea I was talking about right there, where we get a lot of life from. Up here in Siberia, which has been hanging out by itself for quite a while. You see that big orange section there? That's what we call the Siberian Traps. That is a deposit of lava on the surface. Yeah, lava covered that much area in this series of volcanic eruptions at the end of the Permian. We're not sure if this is what caused the extinction, but that much lava getting spat out onto the surface would have meant, think about how many gases and how much ash got pumped out into the atmosphere as a result of the eruptions that put that much lava out onto the surface. This seems like the most likely corresponding event to have caused this extinction. Okay? So, that's the thought process there. Let me go back here. Nope, back. Oh, I guess I covered everything on the previous slide. All right. Now, tectonically, let's talk about Pangaea. Pangaea is a supercontinent And what do we know about supercontinents? It's a lot of landmass in one area. What tends to come as part of that package? Deserts. Remember, we learned this is one of the reasons why you'll get a desert. Interior continental deserts happen wherever a large amount of landmass is cut off from proximity to water, evaporation sources, like the ocean, okay? So it's the reason why there's a giant desert in the middle of Australia. It's a big reason why there's one in the middle of northern Africa. It's a big reason why we're here in a semi-arid environment, because we're so far from any water source that provides evaporation, right? So we get massive deserts that form here in Pangaea, okay? Pangaea on the inside is very, very dry. It's rainforesty out on the coastal areas and here around the Tethys, but very, very dry in these larger sections here in the middle, okay? We get a lot of desert deposits from Pangaea.
What was that one that you mentioned? What's the Absaroka Cratonic sequence?
Oh, the Absaroka Cratonic sequence. Thank you for reminding me of that. Okay, so during the Absaroka Cratonic sequence, remember a cratonic sequence is when we have high sea levels, which means that we get a lot of ocean sediment, like marine sediment, deposited inland, okay? So what happened here is because we have so much dry area, right, that means less plant life, less oxygen in the atmosphere, more greenhouse gases develop, especially as a result of what's going on here with those volcanic eruptions, pumping out greenhouse gases into the atmosphere like there's no tomorrow, right? That led to, at the end of the Permian, we get this big hot event, okay? So all that heat melted the ice that was down here. Let me go back to a couple of slides here so you can see. Look, right here. All that ice that was down there at the end of the Carboniferous, to go down here to the end of the Permian, that's all gone, okay? Sea levels rise, a whole bunch of land gets flooded, we get a cratonic sequence where all that marine sediment gets deposited on top of land, okay? So that's what the Absaroka Cratonic sequence is. The Wichita orogeny, which we already talked about, is what was responsible for making our current situation here in the Permian Basin. As that mountain range was forming, it caused what's called fault blocks. Okay, the collision of the two supercontinents here, the Laurentia and Gondwanaland, created fault blocks, which is essentially where you get a block and a valley, and a block and a valley, and a block and a valley, like this, okay? So here, where we are in the world, we have the Wichita Mountains right here, creating a fault block complex out here to the west. So there's a fault block here, there's a fault block here, there's a fault block here, and right here, between these two fault blocks, becomes the Delaware Basin. Right here becomes the Midland Basin. Collectively, we refer to this area in general as the Permian Basin, okay? Most of what we go and get oil from technically comes from the Midland Basin, which is in this general Permian Basin zone, okay? So that basin developed between those two blocks, filled with water. Sediment piled inside that was washed off of the Wichita mountain range down there, okay? Filled that all in. And that's the sediment that we're working with to get all the oil out of now, okay, from that old basin. Right, then we have the Sonoma orogeny, which is when a whole bunch of, so there were some collisions of islands out there on the west coast of Laurentia, which pushed thrust faults across from the west coast out over here. And that's what started making a lot of the ancestral Rockies. It's what's responsible for a lot of the volcanic activity in northwest Nevada. Okay? That was the Sonoman orogeny. Questions about that? All right. Well, that's what I've got for lecture today. Let's talk real quick about your labs. Everyone has had access to all of the labs for a little bit now. I'm going to be going through and grading everything today. It's my big grading catch-up day, as every Monday is. If you have not done labs, get them turned in ASAP. I would really like it if next week you are only concerned with keeping up with lecture and getting ready for the final. The more lab work you get done between now and then, the better. So let's use today for the rest of class period to maybe turn in as much of that material as possible so I can give you some feedback and you get second or even third attempts done. Yeah. Any questions about the Carboniferous or Permian or anything at all? We are getting into dinosaurs on Wednesday. Yes, we are now set up for dinosaurs because those pelycosaurs are the ancient reptiles that are going to be the ancestors of the dinosaurs. Okay. We good? All right. Well, I will end the recording here. Actually, before I end the recording, I want to tell my online students, a week from today is when we will be doing the final exam review. Please record whatever questions you have for that review and send them to me in an email no later than Sunday evening coming up in 6 days so that I can see those emails and answer your questions for the review on Monday. Okay? All right, now I will end the recording. That's great. Well, it looks like it's been pointing at the wrong side of the screen for a little while. I wish I could control the zoom in function. It's too sensitive. But hopefully you were able to follow along in the PowerPoint as I was talking. Yeah, that looks like what we're going to have to do here. I'll try and keep a closer eye on where it's pointed in the future.